Hello friends, my name is Ankush Kaul and this is my third video on this channel and I'm planning to bring more and more videos for you guys and reveal more and more mysteries about physics. So today I have created a very short and theoretical video on the real source of magnetic field, and what I would like to highlight today is I did some research and it took me some 5-6 days to find out that there is a very common question which is being asked by students, and that common question, if I reveal it here, that common question is this: why a moving charge produces a magnetic field? Okay, so and I have gone through various videos on this, and when I have gone through almost 20-30 videos which are very popular and famous, and when I went through those videos I got to know that people are using very complex terms which students or friends like you won't be able to understand because of the complexity of the terminologies they are using, and also maybe uh, I found that few videos were not giving the in-depth details, or they were hiding some things from the students. So I would like to cover some theoretical aspects of why a moving charge produces a magnetic field. So students, let's start without wasting any more time. So we need to understand magnetism at two levels. The first level that I'm catering to here is the classical level, right? The classical physics level. Cool. And the second level that I will reveal later. So as per this classical level, I'll take you through the chronological events that have happened in history. So students have been asking, sir, why an electron produces magnetic field? Okay, so in 1820, Hans Christian Ørsted conducted an experiment wherein he observed that a magnet experiences some unknown force when placed about a current carrying conductor. This observation basically struck some chords from Newton's laws of motion. And as per Newton's third law of motion, every action has equal and opposite reaction. Correct, students? We know this, right? And this would mean that if a magnet is placed about a current carrying conductor, uh, and you know that magnet experiences a force, then the wire should also experience a force from the magnet, which we can call as a reaction force. If I apply if I kick a rock, I will feel pain because the rock exerts a reaction force back on me, right? So, so something like this, we can understand it in this very simple terminology that, you know, um, magnet experiences a force in the presence of a current carrying conductor. So a reaction should also be there, that a current carrying conductor should also experience a force from the magnet. Second point is, now coming to the nature of this force, what should be the nature of this force? As we know from our, knowledge, what we have been studying in from our, fifth class onwards about forces and all. So there can be two possibilities. Either this force is gravitational in nature, or this force is magnetic in nature. But why can't it be gravitational force that moves the magnet? Because when I place the magnet in the neighborhood of a current carrying conductor, the magnet moves. Maybe it rotates to left or right, or whatever happens, it moves its position. So why can't this motion be because of gravitational forces? So it's just a probability or a chance. I will tell you two reasons why there is very bleak chance or very less probability that the motion is not due to gravitational force. The first is that the gravitational forces are always attractive in nature. Now imagine you have placed a magnet and it rotates in such a direction that it seems as if the magnet has got repelled from the wire. So say if I draw a wire in this direction, this is a current carrying wire, it carries some current, say 2 amperes. And say I place a magnet here. Cool. So this is my magnet, students. Now what if the magnet rotates in this direction? So it repels away, correct? So if it repels away from the current, this force cannot be gravitational force, because gravitational force is always attractive in nature, right? This is one you can say affirmation from my side. And second thing is from the theory of fundamental forces, which was laid down in 16th century and earlier. we have four fundamental forces in nature, right? One is called as the strong nuclear force. Second is called as the weak nuclear force. Third is called as the electromagnetic force. And the weakest force is the gravitational force. So gravitational force is the weakest force in the universe. If it is weakest force in the universe as compared to, if I draw their strength, portfolio, then if I draw the strength portfolio, then we'll have strong nuclear forces, then we have electromagnetic forces, then we have weak nuclear forces, and gravitational forces are the least strong, as we say, right? So again, you can say the electromagnetic forces are stronger than gravitational force. So if magnet moves, there is a high probability that it is because of some magnetic force and not the gravitational force. So this is something from the classical level. If you want to understand magnetism at a classical level, that why, because what students are asking is, sir, why current carrying wire produces magnetism? Now students understand, a current carrying wire exerts a magnetic force on magnet, because a magnet can only move under the influence of two forces, gravitational or magnetic. Gravitational, I have shown you why probability of this force being gravitational is very small. Hence the only force left is a magnetic force. That means the wire is exerting a magnetic force on the magnet which is kept in its neighborhood. From Newton's third law, the magnet should also exert a reaction force on the current carrying wire. And the nature of the force should, again, the reaction force nature should also be magnetic in nature. And if that is so, that means the current carrying wire must contain some magnetic character. Though it is a current carrying conductor, it's not an iron block which can be considered as a magnet. Okay, so but because it throws away magnetic force in its surrounding, and it also absorbs it as a reaction force, so it should have some magnetic character. This is one evidence, right? And a current carrying conductor, when I say current is flowing, so friends, flow of current is nothing but it means electrons are moving in a particular direction. We generally, the convention is to show direction of electrons opposite to the direction of current inside this conductor. Okay, so the black arrows I'm showing as direction of current. Now let's move to the other aspect, understanding magnetism at an atomic level. Now when I understand magnetism at an atomic level, so what happens? Quantum physics comes into picture. What is quantum physics? It's a very complicated physics, first of all, and it's not as easy as classical physics. We need to do we need to do a 2-year 3-year course program in this quantum physics, and then we can understand the realms of quantum physics. So why it was introduced in nature is, wherever classical physics failed, we had to go to some other pillar to save ourselves from the clouds of uncertainty. So with time and with intelligence of the previous scientists and all, we have deduced this quantum physics, right? So quantum physics gives us answers to all the unanswered questions from classical physics. So there was a great quantum physicist by the name of Mr. Erwin Schrödinger who received a Nobel Prize in 1933. And he postulated in 1925. Now understand it, 1820 Oersted did that experiment with the help of classical physics, and after almost 100 years, in 1925, Schrödinger formulated an equation which is called as Schrödinger's equation. And the name is very tough, and I'm an Indian, and so it's a tongue twister. So for Mr. Schrödinger, so what happened, his equation gave the position, it's mentioned here, you can see the position, energy, nature and movement of any electron is governed by 4 quantum numbers. Okay, so Schrödinger's equation gave a solution were 4 quantum numbers. I'm not going into the details of those 4 quantum numbers, but I will only talk about one quantum number which is important for us to understand magnetic field. Okay, so these quantum numbers basically told us about the position of an electron inside an atom, energy of an electron inside an atom, nature of that electron inside an atom, and in which direction or what kind of movement this electron is doing inside an atom, right? So there is another great quantum physicist by the name of Richard Feynman, who received a Nobel Prize in 1965, almost 32 years after Schrodinger's Nobel Prize, right? So when he was asked, because he was also a great quantum physicist, when he was asked about this Schrodinger's equation, I'm just trying to tell you how complex it is to understand this equation. Feynman replied by saying, uh, where did we get that equation from? Nowhere. It is not possible to derive it from anything you know. It came straight out of the mind of Schrodinger. So even Feynman had some inhibitions, in or we will say in actually digging deep into what Schrodinger had calculated. But his results matched up with the other results which were already obtained by, if you remember, we had a scientist, Mr. Bohr, okay, and he also gave us various results regarding the position, energy, nature, and movement of electron inside an atom. So Schrodinger's equations solutions were in coherence with the Bohr's atomic model. Right now, our main point here is about magnetic field. So one of the quantum numbers is called as magnetic quantum number, and this quantum number depicts a very important effect in atoms, and that effect is called as Zeeman effect. Zeeman is name of another scientist. Zeeman effect was formulated. It was an experiment which was done by exposing an atom to an external magnetic field with one intention in mind, that let's see what happens to the electrons of these atoms, right? So Zeeman effect states that an electron in an atom experiences a shift in its energy level when the atom is placed in the external magnetic field. Now understand, why would I why would I experience a shift in my energy when I'm being placed in an external magnetic field, unless and until I have, some kind of relation or resemblance or some kind of feeling for the magnetic field, or I have some inhibited magnetic character inside me. I have some magnetic DNA, right? So this was another experiment which was done to see why an atom basically, or a moving electron, shows a magnetic character. Because very very frankly and very simply saying, students, if I have this pen in my hand, if I drop it, right, it will always go in the direction of gravitational force, because gravitational force is pulling it downwards. It is attraction here. But why it goes down, there is a much deeper reasoning behind that. The deeper reasoning is, anything in this system wants to achieve minimum energy state, a state in which it can find itself stable. Stability comes when you have minimum energy. You sleep when you think you are very low on energy and you want some rest. So everything in this universe, nature has designed it in such a manner that everything in this universe wants to, always achieve stability, and always go from, or go from a region of higher energy towards a, not go, but have a desperation to go from a region of high energy to a region of low energy. Whether they are going from high to low or low to high, that is one thing. But if the energy is changing, if I drop this pen, initially it is at a height of edge, it has some potential energy. When it hits the ground, its potential energy has reduced. Now it has low energy. So it has moved under the, I just dropped it. I have never thrown this pen downwards. So when it hits the ground, it has some low value of energy with which it hits the ground, correct? To achieve stability. So similar kind of understanding can be made for electrons. When when and for this pen, it has a gravitational character, mass, it has weight, correct? It has weight is a gravitational character. So same way for this electron, if this electron shows shift in its energy level when placed in an external magnetic field, it somewhere relates to the reaction force that the current carrying wire undergoes in the presence of a magnet. A current carrying wire in the presence of a magnet, current carrying wire, inside the current carrying wire we have electrons. So these electrons experience a shift in their energy states. Why would my energy change when I am put in a gravitational field? Because I would like to, achieve stability. I would like to shift my energy from higher to lower energy regions. So this is again a quantum wave of understanding why electrons possess a magnetic character, or an atomic wave of understanding this. And if I take you further onto, you know, something that is more interesting towards the conclusion of this video, that I would like to say that many texts, many videos, many books prove that magnetic field can only be understood from the theory of relativity, which was formulated by Albert Einstein. As because relativity talks that one body is moving with respect to another body, right? So similarly, students, when you have a current carrying conductor, you have electrons moving in it, right? And we say that the basic notion of magnetic field comes from that only a moving charge, correct, only a moving electron can produce a magnetic field. Okay, so the electron must be moving. If it is moving, that means it must have some relative velocity with respect to some observer, and that's where theory of relativity comes into picture. What theory of relativity explains, I'm not going to tell you that, because that is more of a technical terminology where I don't want you to get confused. I have spoken heart to heart to you to make you understand that why an electron, what have been the previous chronological observations through which we have observed that an electron has some magnetic character. And towards the end, students, an electron orbits as well as spins inside an atom, and hence an electron is always moving with respect to its nucleus, and so an atom can always be considered as a source of magnetic field. Hence, apart from the already existing electrical field, because every charged particle, electron, proton, creates a electrical field also in its surrounding. So apart from the electrical field, these electrons also produce a magnetic field, because they are every time orbiting around the nucleus and spinning about their own axis. So anything, my dear friends, my entire intention of this video is to let you know that if we observe anything around us and draw our conclusions based upon keen observation, things become very simple, and we also can reach to higher degree results like what Oersted and Zeeman did in their experiments. And with this note, I would like to thank all of you for listening patiently to me, and I hope some things have gone into your mind, and this might help you to solve the mystery that why a moving charge produces a magnetic field. Towards the end, I would also like to mention, if this is the case, this means that every atom in this universe has a magnetic field. Every atom in this universe has or produces an electromagnetic field in its surroundings. And it is the interaction of electromagnetic fields of two human beings when we decide that I like a person or I dislike a person. Their aura tells us. Aura is a term which is used, not a scientific term, but it is more of a literal term, right? And in physics we don't say aura, we say the electromagnetic field of one person. It looks dirty, so I won't be attracted towards that person, or I dislike that person. But if I find the electromagnetic field, if my electromagnetic field finds that the electromagnetic field of the another person is attractive, it's pleasant, it's peace giving, and it's a happy field, then I would definitely love to talk to that person, and I would develop some kind of likely, some kind of liking for that person, or I may get attracted. So these are deeper emotional details, and they can be covered in some more videos, so which I'm going to present to you in this YouTube channel. So I hope you enjoyed the video and you understood what I wanted to convey to you heart to heart. So thank you so much, all of you, for listening to me, and I will see you soon in my next video. Goodbye.